Okay, chapter 4, heat exchangers. Now, in this video, we will focus more on overall heat transfer coefficient and fouling in heat exchanger. Okay, so first we focus more on the overall heat transfer coefficient. So a heat exchanger typically involves two flowing fluids separated by solid walls. And then heat is transferred from the hot fluid to the wall by convection, and then through the wall by conduction, and from the wall to the cold fluid by convection. So from here, from this statement, we can do the thermal resistor network where there will be two convections process involved. Okay, the first one is from the wall to the cold fluid. This will have a convection process, and the hot fluid to the wall will be a convection process, and we have one conduction resistant. Okay, if we are doing the thermal resistor network, so we have here, now we have hot fluid inside the tubes. This is double pipe heat exchanger where there will be annular space in between outside tubes and inside tubes. Okay, this is what we call as annular space. So we have hot fluid inside this inner tube, and then cold fluid will be in at flows in the annular space. So here we have, if we can take a look at this, we make it we make this point or this area enlarge, so it will be like this. So for example, this this figure shows that the hot fluid will be in the inside tubes, okay, and the cold fluid at the shell tubes, shell side. So annular space for the double pipe heat exchanger also called as a shell side, okay, or more specifically annular space. So we have to enlarge at this point. So we have hot fluid inside and then cold fluid outside, okay, and we have another this is the outside tubes, okay, with a thickness. Okay, this is this one, outside tubes. Okay, so from hot fluid we will have a convection process to the wall of these inner tubes. Okay, so this is the surface inlet for the inlet tube, inside tube. Okay, so the convection process will occurs at this point, and then from this point to this point, this is thickness of the tubes, inside tubes, and then the conduction process will occurs at this point. Okay, and then we have another point where from this wall, okay, inside tube walls to the cold fluid, there will be a convection process occurs. So we have one convection, two convection, and one conduction process. So if we do the thermal resistor network, it will be like this. From the T inside, where the hot fluids, so this Ti is hot fluid, and then this is convection process. So the convection process is 1 over HI. So HI represent inner convection heat coefficient. So AI is for the area inside, okay, AI, inner area from the first tube, okay. And then the second one is R conduction, so resistant conduction, so R wall. So we have R wall, and then for this point, for this the last thermal resistor network is for the convection process, where from the wall of the inside tubes to the cold fluid. So we have RO. RO means R outer, resistant outer for the convection process, and then convection resistance is 1 over HO. AO. HO represent outer convection heat transfer coefficient, okay, and AO is for the area outer area. So you have to use area here is area where the heat transfer occurs. So AO here is the area you will use the diameter for outer diameter of the inner tube. Whereas for the AI, you will use the inner diameter of inside tubes. Okay, we will have two different areas. So you will not take the area of this, the area if we can enlarge at this point. So we have two different area. AO is not this one. This is not the area for AO because we are not dealing or we are not calculating the rate of heat transfer at this point to the outside fluid. For example, air. We are not calculating that. We are only focusing more on the transfer of heat from the hot fluid to cold fluid. Do not calculate for the resistance occurs at this point. Okay, this point. No. Okay, we are doing our analysis on the inside tube to the cold fluid. So the cold fluid is in shell tube, shell side, or we call it as annular space. Okay, for a double pipe heat exchanger, the thermal resistance of the tube wall is, we know that this is cylindrical in shape. So we have to use resistance for the conduction. We are use a cylinder resistance. Do not use flat plate. So we have another conduction resistance equation. Am I right? R equal to L over Ka. This is only for a flat plate. Okay, flat plate. Do not use this equation in order for you to calculate the resistance of the wall of the inside diameter, inside tubes. Do not use the flat plate resistance equation. Use this because we deals with the cylinder shape, cylinder tube. Therefore, the equation must be ln d outer over d inner divided by 2 pi KL. This is the right equation for the cylinder or for the tubes. For the tube, okay? And then the total thermal resistance, we know that we already draw this thermal resistance network. Therefore, we want to calculate what is the R total. So R total is Ri plus R wall plus Ro. So if we deals with the parallel arrangement, therefore you have to calculate the resistance for the parallel. For this case, we are dealing with in series configuration. Therefore, the R total is the summations of Ri, R wall, and Ro. Okay. So the R total is Ri plus R wall plus Ro. Then we just sum up all these. So put up, fill in all those values inside this equation, and then Hi and H out. So at this point, as you can see here, we have Hi and H out. So sometimes these two values will not be given, or either one of these value will not be given. That's why you learn from the previous chapter how to calculate the heat transfer coefficient. And that knowledge will be applied to this chapter, heat exchanger chapter. So Hi is, as we know that, take a look at this figure. Hi is inside of the tube. So we will use the method of internal force convection method. That's why you learn internal force convection before. So in order for you to calculate what is the heat transfer coefficient. Okay, what about HO? HO is annular space, and I will explain more on how to calculate the annular heat transfer coefficient. But at this point, HO is external force convection. Okay, external force convection. But for the annular space, I've introduced you with the annular space in internal force convection because it combines, because we have two tubes and that tubes is internal. Okay, like this. So we have tubes and there is another tubes outside. So this annular space, okay, is internal force convection. Okay. Okay. For the double pipe heat exchanger, this annular space is for the internal force convection. Therefore, H out here is for the internal force convection. If you are dealing with the shell and tube heat exchanger, this H out is falls under external force convection. Okay, this equation I put it HI for the internal force convection and HO is for external force convection. This applies for the shell and tube heat exchanger or cross flow compact heat exchanger. Okay, for a double tube, both of these values falls under internal force convection because H out is annular space. Okay, this annular space, if you refer to my previous video, not previous videos in internal force convection, you will notice that this annular space is falls under internal force convection. Okay, you don't have to worry because I will teach you on how to calculate heat transfer coefficient for the double pipe heat exchanger in the annular space. To make you understand the calculation, I will focus on the explanation on the example. Okay, I will focus more on how to calculate the annular space heat transfer coefficient in the example. Okay, when one fluid flows inside the circular tube and the other outside of it, we have, so pi 1 is pi dil and A outer is pi d outer L. So like I said before, we have a double pipe. So now we focus more on double pipe only. So we have these kinds of configuration for the double pipe. Sorry, the figure is not well in shape, perfect in shape. So let's say we have these kinds of figure for the double pipe heat exchanger. Okay, we have two tubes inside with a thickness. Okay, for the DI, you will not calculate the area at this point. Okay, I change the color to make it more presentable. So do not choose diameter inlet at this diameter because we are not calculating the diameter at the outer surface of this at the outer tubes. Okay, the outer tubes is not in our calculation because we are not calculating the heat transfer from cold fluid to outside. If we are dealing with this rate of heat transfer, then DI will be here. But now we are focusing more on the heat transfer in between hot fluid inside the internal tubes and then annular space. So therefore the area, the diameter inside will be here. So this is diameter I and diameter out is here. So D out. Okay, because you are only focusing more on the heat transfer between internal tubes to the annular space. Okay, do not calculate area inside by using the diameter inside of the outer tubes. Okay, that is the equation for the area 1 and area 2. Area out, AI and A out. So the equation that will be used is surface area equation. Do not use cross-sectional area because you are not dealing or you are not calculating the mass flow rate for the fluids. You are dealing with the heat transfer, rate of heat transfer, or you want to calculate what is the resistance for that surface, okay, where the heat transfer occurs. Do not calculate cross-sectional area, because cross-sectional area normally for the mass flow rate or discharge rate, volumetric flow rate, okay. So this is the figure, the same as what I've told you before for the inner tube and outer tube. Okay, it is convenient to combine all the thermal resistance in the path of heat flow from the hot fluid to the cold one into single resistance. Okay, now we have R total is Ri plus R wall plus Ro. So we have R total terms. Now we want to combine all those R into single resistance. So how? So we know that Q dot is delta T over R. R is R total. Okay, now we want to change into single resistance, where we will use this one, UA. So U is overall heat transfer coefficient. So this is what we call as overall heat transfer coefficient. A is area, surface area, delta T is thermal gradient lah. And then is equivalent to UI, AI, delta T, and equivalent to U out, A out, delta T. So I will explain to you why does this equation becomes UI, AI, delta T and UO, AO, delta T. So let's take a look. Okay, U is the overall heat transfer coefficient and unit is watt per meter square dot degree Celsius. So by cancelling T, equation 11.3, this equation will reduce to, so we have 1 over UAS equal to 1 over UAI equal to 1 over UO, AO is equivalent to R. So this R is actually R total. Okay, R total is, previously we already wrote down the equation for the R total. And then this is equivalent to 1 over U naught A naught and equivalent to 1 over UI AI. And R total here so R total is equal to 1 over UAS. Okay, U is overall heat transfer coefficient times with surface area. So if you want to change, you don't want to use the R terms, then you can change it into overall heat transfer coefficient terms by substituting R total with 1 over UAS. So you have this and substitute inside this, it will become this. Okay, this point or this equation I will explain later. Why does this becomes like this? Okay, because we know that if we are talking about the R total, we are calculating the overall heat transfer coefficient. Why does this equation is only refers to the overall heat transfer coefficient inside of the tubes and this overall heat transfer coefficient for the outer tubes? Okay. So when the wall thickness of the tube is small, okay, when the wall of the tube is small, thin, previous example, as you can remember, we are dealing with a small thin tubes where the diameter inside is equivalent to diameter outside. That is our assumption. And at that point, the wall thickness is negligible. Okay. For the when we neglect the tube thickness, therefore there will be no R wall. Okay, the conductivity will not be there. Thermal conductivity of the tubes is high, and then the conduction process will not be occur. We are neglecting the conduction process at the wall of the tubes. Okay, because there is no thickness. Okay, we are assumed that D inside is equivalent to D outside. Therefore, we will neglect the conduction in the wall of the tubes. Okay, and the inner and outer surface of the tubes are almost identical. So because of the small tubes, because of the wall thickness is thin or small, then we are assuming that the diameter inside, okay, we are assuming that DI is equivalent to D out. So from this assumption, we can say that the area is almost identical. So AI is equal to AO is equal to AS. So the equation 11 for 4, so this equation will reduce to 1 over U equal to 1 over HI plus 1 over H out. So this equation, so we know that the area, the wall thickness is thin, therefore AI and AO is equivalent, identical, am I right? So AI and AO is identical, therefore we can cancel out the A terms. So the equation will becomes 1 over U equal to 1 over HI plus 1 over H out. Okay. Then when HI is much more greater than HO, so what will happen to this equation? 1 over U is equal to 1 over H out. Okay. So for example, this condition, we know that HI is much more greater than HO. So we have 1 over H out is greater. HI is greater 1 over big number. So big number plus 1 over HO. So 1 over big number will be smaller. It will shows a smaller number because 1 over big number. For example, 1 over 1,000, it will be 0.001. Okay, 1 over 4, H out is 4. For example, let's say HI is 1,000 and then HO is 4, for example. So if you divide, so 1 over U equal to 1 over 1,000 plus 1 over 4. This value much more greater than this value because this value will be 0.001 and it is much more greater than 1 over 4. If you calculate 1 over 4, okay, 1 over 4, you will have 0.25. So this value is too small. Therefore, we can neglect this. We are neglecting this value. Or in other words, we are neglecting the terms 1 over HI. So we neglect these terms and then this equation will become 1 over U equal to 1 over HO. Okay, approaching to 1 over HO. Because 1 over HI is too small. Therefore, we can neglect. So there will be another condition where we have HI is much more smaller than HO. What will happen? Again, the same as before, like this. So if HO is much more greater than HI, therefore 1 over HO will be too small. Then we can neglect 1 over HO. We have only 1 over HI. Okay, this equation will become this equation. For the second condition, we will neglect the term 1 over H out. Okay, therefore it will become 1 over U approaching to 1 over HI. Okay. It doesn't matter if you want to calculate 1 over HI because that value will not give a significant impact or significant effect to your calculation because it is too small. and it can be neglected. But if you want to calculate it, it depends. It's up to you. You may calculate that value if you don't want to neglect that terms in your equation. So it depends on you. You may assume that 1 over hi is equal to 0. So you may cancel out that terms. Or you want to calculate, it is also okay. Then we go to the fouling factor. What is the fouling factor? So the performance of the heat exchanger usually deteriorates with time as a result of accumulation of deposits on the heat transfer surface. So this accumulation will create an additional resistance to your rate of heat transfer. So because it will have a thickness, okay, and it will wraps around your tube, inside tubes or outside of the tubes. When it wraps outside of your tubes or inside of your tubes, it will create another resistance. The resistance comes from that accumulation of deposits. Okay. If there is deposit or accumulation of deposits, if there is an accumulation of deposit in your inside tubes and outside of the tubes, you have to include the fouling factor, which is here is RF, the net effect of this accumulation on heat transfer. So two common types of heat fouling. One is precipitation of solid deposits in a fluid on the heat transfer surface, or another one is corrosion and other chemical fouling. So this is the figure of the fouling. Maybe this is the figure from inside of your tubes. There will be a deposit of minerals or chemicals on your tubes, okay, on the tube surfaces, and this deposit will create additional resistance. So in your equation, so the overall heat transfer coefficient needs to be modified to account for the effects of fouling on both inner and outer surface of the tubes. So for the unfilled shell and tube heat exchanger, it can be expressed. Now we have previously, we know that the R total without fouling is 1 over HI plus ln D. Okay, this is our previous equation without fouling. So we have this term. One is a convection inside, and then we have conduction, and we have convection. So this tube. So if I can draw here, so I draw here. So previously we have this convection, and then conduction, and then convection. So what will happen? So we have fouling. When we have fouling, there will be a deposit on tube inside tube surface and outside of the tube surfaces. So the red represent the deposit of your chemicals or any minerals, okay, that deposit on your tube. So this deposit will create an additional resistance. Okay, therefore the equations that previously we know that there will be a 2 convection and 1 conduction. If there is a fouling inside and outside of the tubes, and we have to include this term. So this is inside fouling, okay, and this is the outside fouling. So the resistance inside and outside, okay, if there is a fouling inside and outside of your tubes, so you have to add another terms, fouling inside and fouling outside. Your R total will become like this. Okay, so RFI and RFO is fouling factors at those surfaces. So that is all about overall heat transfer coefficient and um, fouling factors. So